Welcome to PlanetGeo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. I gotta hit record on this one. So, okay, we've got to back up, Chris. Okay, so for
you
for
never know what you get
for
with
the
me,
listener that's just joined us here to this very exciting podcast. My camera's out of focus, so when it does that, I kind of stick my hand near the camera to try and get it into focus, to get it to focus on something. Chris, you just go, wait, you have this thing on your hand. And I've always thought it's a callus. It's like a callus kind of in the near my like ring finger on my right hand. Like, you know, on
how
my
long
palm.
have you had this callus? Like forever, right? You've had it.
Yeah.
Yes.
All my other calluses have kind of gone away or come back. And that one's always been there. And you, what is it? It's something, you just went to your skin doctor and they told you
I
it's
went to my
something?
skin doctor and I'm like, hey, can I have this callus removed? And he's like, that's not a callus. I really should know what it is because I want to get it taken care of.
Well, I want to describe it the way you just described it, which was a Scandinavian disorder.
Yeah, it's something like that. Yeah.
This is amazing. I'm learning so many things about myself by doing this podcast with you. I have a Scandinavian skin disorder.
You actually do, and you should get it taken care of because it'll cause your tendon to contract, so you'll lose flexibility in that finger. So it's your ring finger on your right hand.
Yeah, it's the ring finger.
That's where it is.
Wow. Okay, I'm gonna have to go get this dissolved or taken care of in some way.
Yes. So I've known about this for 2 years.
Have you gotten it taken care of?
No. I keep forgetting about it.
Yeah.
And
because it's just
and
like
I just went and saw him, and I wanted to ask him about it. Like, what's the name of that again? Because he recommended that I go to an orthopedic surgeon, and they put an injection in which dissolves whatever you and I have going on.
Amazing. This is great news. Okay, wow. A diagnosis on PlanetGeo here. This is great. This is good.
Yeah, I know. You should ask your doctor wife about this.
I will. I'll ask my doctor wife, and she'll probably say, "Don't worry about it." And then I'll ask the orthopedic doctor next door and be like, "He'll inject me. It'll be great. He'll dissolve my problem." Yeah. Oh my goodness, I love that. Okay,
look at me fixing your problems.
You're fixing stuff. I mean, this is the biggest contribution you've made to this podcast in a long time, Chris. Well done.
That's
great.
No, that's not true. That's not true. This is a small contribution, Jesse.
No, that's
I'm fixing your trigger finger.
Today is going to be a big one. Today, I'm excited about this episode. We're talking about Eskers today, and well, I learned from you what Eskers are in high school geology class. Probably even before that, you might even cover Eskers in earth science, 9th grade earth science.
Little bit, really, really basic level. Yes, just to identify an esker, because they kind of look like these really sinuous. They're really cool ridges. I don't know. So that's all.
No, but and then in geology, you taught me the sort of intro level textbook version of an esker, which is, okay, here's how it forms. It's a river, under glacial river that's running, and it kind of gets deposited, this sort of shoestring, sinuous ridge of sediments. That's true, but they're a lot more complicated than that. And I think there's some really important nuances, Chris, because, that description, like, and I'm not saying you teach it this way, but if you're describing it to somebody on the street and you're like, hey, this is what an esker is. If I'm describing to my in-laws or my parents, what is an esker? I say, yeah, it's a glacial river that deposits sediments. You go away and say, okay, that makes sense. Good. But then you go away and think about it a little bit. And there's a couple of like inconsistencies with that singular model, right? If somebody pictures a glacial river, a lot of people listening probably have seen this. Like, you imagine, I just recently saw a YouTube video of some guy kayaking on a river that's flowing on top of a glacier, right? And it's beautiful, looks really risky.
Because it's this really, really blue water. It's beautiful.
Beautiful. But the blue, Chris, it's clean. This is clean water. So it's not depositing anything. And it's also not at the ground. It's on top of this glacier. So, like, the simple explanation, it flies. It makes sense if you don't think about it too much. But as soon as you think about it deeper, it doesn't make sense.
Yeah, exactly, Jesse. But that's everything that you and I do in our intro level classes.
It's
the
true.
Stuff that we teach, really, all of it is nuanced. And none of it is quite as we depict it for this classic textbook model, going right on back to, how does granite form?
Yeah, totally.
Well,
Yep.
It's the same thing.
It's the same thing. The granite one, you can go a long time without realizing the inconsistencies in the granites. I think you just got to think about eskers for about 5 minutes and then be like, okay, wait, how does this doesn't make sense. This is a little counterintuitive.
Well, let's go back to a couple of basic glacial principles. Glacial deposits fall into two basic categories. You have what's called stratified drift and glacial till, and they're very different. And the feature that we're talking about today with Eskers, it's a deposit that's made of stratified drift. In other words, this is sorted. It has rounding. It has everything that any other stream deposit would have, because water is very discriminating in terms of it can only carry certain size particles dependent upon the energy of the water and how fast it's moving and so on. Whereas glacial till is sediment that's deposited directly by melting ice. And ice is all inclusive. Ice doesn't care. It can carry anything. It can carry a boulder the size of my house and a grain of sand, and it doesn't discriminate between them. And it also doesn't do much rounding. So you don't have any sorting. You have no rounding. It just, wherever it gets plopped off, it gets plopped off. And so they stand in stark contrast to each other. Glacial till versus stratified drift. Strata implies water and layering and sorting and everything else that water would do.
If you picture a continental scale glacier, huge glacier, many miles thick, where it starts to melt, it's a conveyor belt. It's like a massive conveyor belt where you get a conveyor belt at your grocery store. If you just dump your groceries on there, the conveyor belt is not discriminating. It is just dumping groceries off in a pile at the end. It's just going to keep going until they pile up at the end. That's what's happening with a glacial system that's forming till. So it dumps this blanket of till, relatively continuous blanket of till on the landscape. So if you go up to northern Canada and Michigan too, you'll see glacial till deposits they don't have a ton of variability across them. It's kind of like a big thick blanket of unsorted sediments. Eskers are, as you said, water deposited sediments. Let's dive a little bit more into the details here. The esker is a depositional feature from a stream. And the stream is forming, the water in the stream is forming from melting glacial ice. But we have to think, here's where the kind of nuances come in here. We have to think, where, Chris, does a glacier melt? Where on the glacier is it melting? And I think it's kind of maybe potentially obvious. Is this an obvious one or not?
I think so. Glacial meltwater is in abundance near the margin of the glacier, because that's where it's warmer. Whether that's, in alpine regions at lower elevations or continental ice sheets where it's, think about Greenland. Most of the glacial meltwater is going to be near the ocean, near the edge of the continent where the glaciers are terminating, where they're kind of ending.
That's right. And it can be seasonal. In the summertime when it starts to warm up, the top layer of the glacier near the air is going to have more seasonality to it. It's going to warm up, start to melt in the summertime, produce meltwater. That meltwater is going to flow downhill, which on a continental scale, we'll come back to this, but on a continental scale glacier, it's away from the center of the glacier. Think of the glacier as an ice cap or an ice sheet where it's thickest in the middle, it's thinnest on the outside, kind of like a pancake. You put your thick pancake batter on the pan and it kind of spreads out. That's what the glacier is doing. So it flows downhill, which is kind of radially outward from the center of the glacial ice sheet. So it's flowing out there, but it's clean water. Think of that visual of some kayaker kayaking on glacial meltwater river. It's clean. There's not much sediment in that thing. And it's also not on the ground surface. So it's not depositing anything on the ground surface, and if it could magically deposit something right below itself, the glacier would scrape it away. So we would lose that record. So how do we get that water that's on the top of the glacier to do the depositing of the esker that we're going to talk about?
Well, we have another intermediate step that we have to get to, which is also near the margin of the glacier, near the lowermost elevation or where the glacier is terminating. You also have crevasses and moulins. And moulins are these like vertical shafts or cracks that go from the surface down toward the bottom of the glacier. So you have these very clean streams on the surface, abundant water that then dives down into a crevasse or dives down into one of these moulins to the point where it hits the bedrock, the bottom of the glacier.
And that makes sense, right? Like these cracks go deep. As soon as you dump water into a crack, it's going to, especially an ice-filled crack, it's going to start to melt the ice, erode the ice until it works its way pretty quickly, probably down to the bottom where there's no more ice, which is the bottom of the glacier ice sheet. So Chris, quick question for you. You were just in Iceland. Did you see a lot of glacial meltwater? And did you see any anything like this?
So yeah, what we saw in Iceland were the abundant meltwater coming off. In fact, there was a day that it was near the town of Vik where they had this glacial flood that wiped out the road, wiped out the ring road, and that's the main road around. And so people were stranded because they went to Vik from Reykjavik, and then they couldn't get back to Reykjavik without going all the way around from the south shore, all the way around the north shore back to Reykjavik. So either that or they had to wait a few days till they could open up the road again. So because what they had is I told you about this, lots and lots and lots of rain. And so this is exactly what we're talking about. So yes, abundant water. And what we also saw is abundant cracking near the lower margins of the glaciers. Absolutely. And it was just beautiful.
So did this give you, your trip and what you saw, did it give you a new appreciation for the specific processes we're talking about with Eskers here? How this makes sense, that this model makes sense?
100%. Absolutely.
Yeah, yep. That's cool. Oh man, I wish I could see that. I've seen this not at this scale anywhere near some of the there's like quote unquote ice caps in the Canadian Rockies. They're not huge, but they are alpine glaciers in a serious way. But you don't often see, meltwater in these channels in the same scale. Just they're not the same scale.
However,
as the continental sheet.
There are a lot of YouTube videos that really capture this well. All this meltwater on top of a glacier, beautiful blue, clean water diving down into a moulin. You can get this. It's a real quick YouTube search, and there's a lot of it actually. Yeah. Yep.
That's cool. I'll have to take a look at that. So build upon this story so that we got this glacial meltwater. It hits a crack somewhere, and it dives a crevasse or a moulin, and it dives down in, eventually works its way to the bottom. Now, Chris, the important thing here is we have this pressurization. This is really important for esker deposition, is because, and I don't know the best analogy, maybe it's like a water tower or something, but we have water flowing kind of straight down into the glacier. It hits the bottom.
Well, it has nowhere to go, right? That's where the pressure comes from.
That's right. It's got nowhere to go initially, and it has to sort of melt its way out of that. So there's a ton of pressure, and even when it does, I think it's kind of like a pipe that's flowing downhill. Water pressure in your house, you have water pressure because there's a big water tower nearby that's putting the water up high. I mean, if you're on city water, that's the source of water pressure. And so that, if you imagine glacial meltwater flowing down through a crevasse, that's a lot of pressure that's building up back there and backing this up. And that's a key part, because water under pressure, especially in ice, will start to do stuff to it.
That's right. Yeah, this pressurization is really important in the development of eskers. But I do wonder about one thing, because I do this with my geology classes, is I want to show the effect that pressure has on ice. Because if you think about it a second, water, when it freezes, it expands by about 9%. That makes water a bit of a chemical freak, because most things, when they go from the liquid to the solid phase, they contract. But water does the opposite. It expands. So if you take two ice cubes, put one on a lab table, and then put the other on the lab table, put a 10-pound weight on it, and just watch what happens. The one with the 10-pound weight melts much, much faster because of the pressure that you're exerting on that ice cube. Because what you're doing is essentially you're contracting the ice, making it more like a liquid and less like a solid. I wonder about the effect that pressurization has on its ability to melt its way through the bottom of the ice.
Yeah, that's a good question. That's a really interesting question. I mean, I would imagine certainly some, right, of the ice at the bottom is certainly under high pressure and probably a lot colder than just the freezing point, right? So it certainly has a bunch, but the important thing is that it is doing that melting for either pressure reasons or just erosion, like think of water erosion, erosional pressure. The important thing is it starts to melt. When it starts to melt, it is gathering all the sediment from the ice. That ice, especially at the bottom, is carrying stuff. It's the ice at the bottom that has done all the scraping from upstream in the glacial system. So it's carrying a bunch of sediment.
And the plucking.
So this is the cool part. And this is where we start to form an esker, is we start to pick up sediment. This ice does a couple of really cool things. Because it's under pressure, it means that it can flow uphill very easily. And I've seen this in eskers, Chris, in northern Canada. We're flying in a float plane or we're driving around in a boat following an esker system. And you can see, you'll be flying along and you'll see that esker goes up a hill a long ways. And it's entirely continuous. You think of a stream. When a stream hits a hill, it'll sit there and pile up water, make a lake. And so the deposit type would be completely different if it was just a normal stream. But this is a pressurized conduit at the base of a glacier. The esker, the deposits we see now, they just go uphill and they don't change at all. It's kind of amazing. Like you look at it and you're like, that can't be a normal stream. That's something different. And it's this pressure that is allowing it to go upstream, and it doesn't change the physics of water flow in any way.
Right. And it's going to continually be under pressure because remember, water is still dumping down into the crevasse or the moulin. So even as it melts its way out, it's still being pressurized. And so flowing uphill, because it's under so much pressure, no problem at all.
Has no issue doing that at all. I mean, it's a really cool thing. And this water is melting the ice around it. It's eroding. It can flow uphill. It can flow over stuff. It can flow sideways. It does all the normal things that rivers do, except it's probably kind of a short one. It's under pressure until it exits the glacial front. As soon as it kind of, I don't know if it spews its way out, but it will eventually flow its way out.
Hold on, Jesse. So let's think about this without like talking about it right away. What happens once this becomes where it loses pressure? What's going to happen to the flow velocity? Just so you think about that a second. It's obviously it's going to lose pressure, some of it anyway, not all of it, but it's going to lower its pressure, which is going to cause the water to slow down. What happens when water slows down?
Dumps its stuff out. It dumps the sediment right out, right? So it'll lose pressure for two reasons. One, it's flowing out. It's flowing out into the open. And two, as this pressurized water is flowing through this, what we'll talk about next is this R channel, this cavity that it kind of cuts for itself. It keeps cutting and getting bigger. So you take a high pressure water in a small little hose and you put that same amount of water through a larger diameter hose and the water pressure drops, right? So that's kind of what's going on too. So we're decreasing the water pressure as it's flowing through this, which is causing it to take all that sediment it aggregated and deposit it into usually a gravelly ridge. Sometimes it's two ridges that are parallel. Sometimes a little more flat top. Sometimes it's really sharp peaked, but it'll deposit all that sediment on its way out of the glacial front.
That's right, Jesse. And the sediment that's going to be deposited is going to be very, very gravelly, as you said, very coarse-grained pieces that are all the way down to sand, too. So you're going to have this, it's kind of like sandy all the way up to gravel-sized pieces. They're rounded, they're sorted. It's this like long, sinuous kind of ridge that follows the path that the water created, melting its way out of the glacier, melting its way out the glacial front.
I mean, this is such a cool process in detail, and it's so different. It's actually so different from a river system. I mean, it's similar in like a very simple way, but so different.
Let's take a step back, Jesse. If we look at this on a regional scale, there's a geometry to eskers. On a continental glacial scale, think about this a second. You have this continental glacier that's oozing out, like you said earlier, this kind of like thick pancake batter you pour in a skillet. It spreads outward from every direction. So what this kind of shoestring esker looks like, they look like spokes on a wheel, if you will. So you can see where the zone of accumulation was for that particular glacier, because the eskers, if you kind of like extrapolate them back, they come to this relatively central point, the hub of the wheel, if you will. So that's another really cool thing.
It's totally cool, Kristen. I'll talk a little bit about our esker work up in northern Canada, but where we were in Acosta, they're flowing basically due west. The eskers are all going kind of straight west. You go 100 miles north of there, and they're flowing due northwest, and that's because of the different ice sheet. The central point of the ice sheet, they're kind of radiating out from the central point. So you can really easily see this as you're flying around. And actually, these eskers, especially up in northern Canada, our floatplane pilot told us this, but eskers used to be, before GPS, they were the main navigational tool of floatplane pilots, and people dog sled racers and stuff, is you get on an esker and you just follow it because you actually knew which direction you were going. And you'd get on and you see an esker and you'd be like, okay, I know that that's pointing northwest, so I know my direction now.
What an awesome Wow.
Isn't that cool?
That's so cool.
And there's like one.
That's amazing.
There's a really like famous esker system. It's a long esker system. It's like 250 miles of continuous esker. That's like the famous navigational corridor one that all the pilots, like if you were going somewhere, you'd be like, all right, I got to go 150 miles along this esker system and then I hang a right. You know, it's that kind of thing. Totally cool, right?
Well, Jesse, let's leave this then and head into this pressure, and the melting creates what's called an R channel. And the name may be a little bit misleading. So why don't you take this, head into what is an R channel and why is it called that?
The second part is easiest. It's called an R channel or a Roethlisberger channel for the author who wrote a paper that described this process. And then, somebody else, some other scientist said, oh, okay, we should call it a Roethlisberger channel or an R channel. But it's
real quick. Hold on. I'm sorry to interrupt your flow, but the reason why I said that an R channel might be misleading is because we often describe river valleys as V-shaped valleys and glacial valleys as U-shaped valleys, and R has nothing to do with the shape of the channel.
Yeah, I know. It was a bit disappointing. I was hoping it'd be a little bit more interesting of a story about why it's called an R channel than a Roethlisberger channel. But anyway, that's why it's called that. This R channel, it's the channel that the river is following at the base of the glacier. So it's this pressurized tube that the river cuts for itself at the base of a glacier. And basically what's happening is we described all the processes here earlier, but it can cut up. River water is under pressure and it's going to follow the path of least resistance, which is kind of, downhill or out from the glacial front, out towards the glacial front. But it's also going to cut up because that's the place where there's the least pressure. So it's like a stream morphology except flipped on its head, because this pressurized water will start to cut up into the glacial ice above it to get more space.
Or melt up into
melt
it
up,
as well.
Yeah, cut, melt up. And as it's doing that, remember, this ice is the stuff that has all the sediment in it. And so it starts to coalesce or aggregate all the sediment from the ice, or really, inherit all the sediment from the ice that it's eroding or melting in this channel. So we end up with is what's called an esker corridor, where you have a single ridge of sediment, and all that's, it's kind of like, Chris, the river scraped all the sediment in from the sides and deposited it in a little ridge. So all the till is gone from near the esker ridge, and it's all in the esker ridge.
Well, we're taking the till, and now it's getting picked up by the water. And as it does this, because till's unsorted, unstratified, unrounded on everything, now it's getting all of the characteristics that any other water. The further it goes, the more rounded it gets. The further it goes, the better the sorting gets, and so on and so on and so on.
So let's play this forward here. Now that water, it's full, it's sorting this stuff, it's rounding it, it's going to dump it in a ridge right near where that R channel is. Like, it's going to start to deposit sediment. As the R channel gets bigger, the water pressure drops, the river starts to deposit the sediment in there because it's losing pressure. It eventually hits the glacial front and flows out into the front of the glacier, and it's going to have lost all of its major sediment. It's going to have lost all the sand-sized pieces, all the cobbles, all the boulders.
Big stuff would have come out already.
All the big stuff comes out. All that's left is the really fine particles. The clay-sized stuff is all that's going to be left in the water. And so what that means is when the river flows out the front, there's no more esker being deposited. The esker is being deposited still in this like ice channel, the R channel in the ice sheet. Once it flows out, then it flows into like a lake or an alluvial fan deposit, and the stream really slows down. Then it dumps the clay-sized particles on itself. So if you have just a snapshot in time, there's no esker ridge when the river water is on top of the glacier. There's no esker deposit being formed when that water hits the base of the glacier. And there's probably not much esker being deposited the first several meters of this R channel. It's only at the later stage that the esker ridge starts to get built up, and then you get an alluvial fan deposit at the outset. So that's like a snapshot in time, which is not what we see in the modern, like we don't go and see that happening.
If you think about it, most of the deposition, the esker ridge begins when it starts to depressurize as it's melted its way out to the leading front of the glacier. So as deglaciation happens, as the ice retreats, the esker then is going to follow the retreating of the ice. So that ridge is going to lengthen backwards It starts at where the glacier was, but as the glacier continues to retreat, the esker then is going to lengthen because that loss in pressure follows the leading edge of the glacier.
Chris, I'm curious on your take on what I'm going to say here. But that process, you just described that process, that the conveyor belt feature of glacial retreat is just so important to making an esker and to making these deposits. So if you play that model out, what you just said, you play it out over time, over 10,000 years of ice retreat, you're going to have, the result is going to be a continuous esker ridge with alluvial fan deposit coming after it, kind of draping over the esker, or sort of on top of the esker poking out of alluvial ridge deposits, which is exactly what we see. We can have 250-mile long ridges, individual ridges of eskers that go back, but that ridge was not deposited at the same time. It wasn't one long river system, or there's debate about this, but it's probably not that one 250-mile long river system under a glacier. It's probably forming as the thing retreats. So, Chris, I'm curious. This is what I'm curious your take on. The intro level esker take is that they are much more rivers than they are glaciers. But this thing that we've just described, this process is actually, I came away after thinking about eskers more deeply, like we have been talking about. I come away with eskers are much more like glaciers than they're like rivers, actually, because this conveyor belt process is so much more important.
Yeah, the formation of the esker is intimately related to the glacier. I mean, I don't know. It's a really good mix of both, I think.
Yeah, it's like it makes them so interesting, such an interesting sort of deep dive into.
Yeah, I mean, you get the pressure because of the glacier. The esker builds from the front to the back because of the glacier, because of the deglaciation, because of the ice retreating. The esker kind of lengthens with that, which, okay, that's interesting thought. I really hadn't ever thought about that before. But one other thing, Jesse, that I want to talk real quickly about before we move into exploration, why all of this is important and why eskers can be very economically important for mining companies, we should say, is the length of the R channels.
Yeah.
Okay. They're basically you have short model R channels and long model R channels. So that's self-explaining.
Let me interrupt and do the visual. We painted a visual of a short version where the river's flowing on top of the glacier for a long time, right near the front where there's a bunch of crevasses. It dives down and then is only under the glacial bed for a little bit right near the front, the leading edge of the glacier. That's the short model or short conduit. The long one is just a longer version of that. The river dives down to the base of the glacier way upstream. And how would that happen? How would you get a river diving down? Like, why is that a viable interpretation, I guess?
The same thing happens just further up in the glacier. You maybe have crevasses there because of what's going on with the bedrock. Maybe there's a rounding of the bedrock and the top part of the glacier can't expand. It's brittle, so it cracks. And so you have crevasses or moulins that develop higher up. And so this process just is the same. It pressurizes the channel. It has to melt its way out. It's a much longer course because of maybe the regional geology caused it to be just a longer course of action.
So I think one thing before we talk about the exploration side again is that I described a long esker corridor, like a 250 mile. It's called the Exeter Esker System. It's a really famous one in northern Canada. That's like 250 miles long, continuous ridge of sediment. The question is like, how do you form that with a short model? Those two kind of seem initially at odds, like a very short 100-meter R channel doesn't really fit with that long of an esker system. But you have to think about how this glacial flow, this progressive nature will happen. As the glacier retreats, that river system dumping down into the base of the glacier will just keep reusing that pipe. That R channel will just get inherited as it goes upstream. And so that's how you get like a continuous ridge, is there's only one active R channel at a time, and it just evolves over time.
That's a little confusing. There can be several R channels at the same time, but not for that esker. Only one R channel for that particular esker. So
really quick, Chris, there's an interesting thing about that is that there's a spacing. You can map, there's a relatively consistent spacing of esker system from one another. In the place of Acosta, it's kind of like 10 kilometers away. And the reason is it has to do with how fast the glacier is melting. If you have more meltwater, you're going to have esker systems that are closer spaced. If you have less melting, they're going to be further apart. And so the spacing is like that's such a cool calculation, I think. You know,
that's another thing that we could go into with this, right? It's like even as deep as we're going into eskers today, it's not as deep as you could go, or even
it's just so crazy.
Yeah.
Sorry I interrupted. Yeah.
No. I was just going to say that the length of the esker is going to go back to what created the water tower effect in the first place, the crevasse or the moulin that it's dumping into. And then new ones will start in a different place, right? But if you have that happening way, way, way back away from the leading edge of the glacier, then you get these long model potential systems.
Yeah, so that's exactly right. Exactly right. So I think, Chris, this leads nicely to exploration use. And these we had talked a long time ago about, well, it's a great story for how useful eskers were in the diamond exploration days up in northern Canada and in discovering the diamond mines. I mean, it's just an amazing story of geological discovery. And eskers were really instrumental to that because they are pulling sediment from nearby. They're not pulling sediment from all over the place. So you can imagine how exploration can help test the long versus short conduit model. And then you can also see, I think pretty easily, how eskers are really important for tracing material upstream. It's kind of like, I don't know, kind of like many stream chasing type things we do in geochemistry. If you have an anomaly somewhere in a stream bed, you know it's coming from uphill, upstream from that deposit, right? There might be a deposit uphill.
If you think about the stuff that gets deposited in esker was once glacial till. This was bedrock that got scraped, it got plucked by the glacial ice, then it got picked up in these R channels and was deposited then, well, I don't know, downstream somewhere, right? But the part that's maybe not intuitive in this is that, well, then all of that stuff gets covered with this kind of uneven blanket that you talked about right at the outset of the episode. So the bedrock is now covered with this glacial drape, this glacial till material. So the esker, if it has certain minerals in it, let's say, then we can trace where is the buried bedrock, what's the source of it. If we're looking for something, let's say you alluded to diamonds, and we find these tracer minerals in the esker that tell us that, hey, this maybe came from a kimberlite deposit, then that kimberlite deposit is now buried, right? But we can zero us in kind of like a bullseye because we know where that came from.
We know
where that
right,
glacial till came from.
We can kind of say, okay, we see the signal, see the signal, see the signal, see the signal. If we don't see the signal, all of a sudden we've gone too far, right? It's got to be downstream from wherever that stopping of the signal is. And it becomes really, really powerful. But we have to really understand this long versus short model too. That has a big impact because if it's actually a long R channel model, then the till is getting mixed and sorted way downstream from where the gold deposit or the diamond deposit is, right? As if it's a short model, till can be transported a long ways still, but it kind of gets diluted quicker, and the esker will have a sort of a narrower window that it's exposed to of the sediment source.
That's right, because water is much more discriminating in what it can carry and then obviously than what it can deposit. It's way more discriminating than ice is.
And the other thing, Chris, is that the esker, where is it inheriting the sediment from? The esker or the river is inheriting the sediment from right at the base of the glacier, which is the most locally sourced sediment in a glacial system. Sediment way up high in the ice could have come from way the heck upstream, but sediment right at the base is most likely from just upstream. It probably picked it up very close by before it gets kind of pulled up into the ice sheet. So it's kind of inheriting locally sourced sediment. And this for me is why I got into eskers and why we spent a bunch of time sampling eskers up in the Northwest Territories, is because we're looking for old rocks, and old rocks are very similar to a kimberlite deposit, for instance. And so we're starting to use the eskers. We can look at the zircons in the eskers and sort of figure out, are there old rocks just upstream? because we don't really care if they're 250 miles upstream, because that's going to be really hard to find, actually. But eskers are kind of this intermediate window into what is the bedrock just upstream, maybe 5, 10, 20 kilometers upstream. And remember, they also inherit this kind of narrow corridor. So eskers get this in the region we've studied, they're kind of every 10 kilometers. So you kind of get a 10 kilometer band where you can look 5, 10, 15, 20 kilometers upstream and get a pretty good idea of what are the ages of the rocks just upstream. And that's a ton of work to go map that, but you can look at the esker sediments and kind of use this to get a rough idea.
I have a question for you.
Yeah.
Did you ever, in your wildest thoughts, ever think that your quest to find old rocks would lead you back to eskers? Let's go back 15 years ago, let's say.
Absolutely not. No. Absolutely not.
I am blown away by how awesome this is. This is so cool. That eskers aren't just cool to look at, and they're not just a cool glacial feature, but they're also economically quite important.
It's I agree with you, Chris. It's just one of these, the story we just told about how eskers form is so cool, first of all. But then they're also so useful. On the other hand, it's a really one of the everything's fun in geology, but this is a pretty fun juxtaposition of sort of storytelling and science and physics and how it works. It's so
absolutely
cool. Yeah.
You know, geology isn't just good, Jesse. Geology is good for you.
I like that. That's a good one. I like that. Where'd you pick that one up? That's a really good one.
I just thought of it. Just popped into my head.
We're going to use that. That's a good one. We're going to make a shirt with that. Geology isn't just good. It's good for you. I like that. That's
I don't know.
Great.
This comes back to the heart of why we started making this podcast back in COVID, is that, you know, not only is geology awesome, but it's also, why should you know about this? I mean, this fits that whole thing.
Absolutely. You know, in those of you in Michigan or in a former glaciated terrain, you can see eskers. There's an esker somewhere. It might not be as obvious as up in northern Canada, but you can sure see them, and they're cool. And even if you can't, just Google an image of an esker. You'll get an amazing one. They're small. They're beautiful. The story behind them, the physics of how they work is just amazing. So I think eskers are just totally cool, and we're using them for research to look, like you said, at old rocks in a way that I would have never ever guessed that this would be where we ended up sampling eskers.
It's interesting. You and I each read a paper to get us like kind of primed to do this episode, and it was really written from the perspective of mining companies need to know as much about how eskers form. They need to know as much about that process as they can, because that then affects where they start to look for what they're looking for.
Exactly. And like, how do you interpret your mineral data or your geochemical data from an esker system? Like, you know, it's a really important thing. And as we're using eskers, we're starting to use eskers to sort of understand the distribution of basement gneisses that are exposed underneath. You know, that might be upstream, they might be covered in till, they might be too complicated to really work on, or it takes too much effort to map 20 kilometers by 20 kilometers, whereas we can take one esker sample. As we start to dive into this data, we're starting to realize, you know, there's always a feedback, because there's a lot more to learn about eskers. And maybe some of this zircon work that we're doing could help inform, you know, how we understand eskers. So there's like always this kind of feedback where you can kind of kill two birds with one stone in a way. So for me personally, it's an exciting avenue of research, and it also gets the ability to learn more about eskers, which are just amazing features. So fun. So
good. Hey, really good idea, Jesse. This was all you. I'm going to give you the credit for that, because I loved diving into this. It was just fun.
And you came, you know, and you were just there in Iceland seeing all this stuff. You saw all the component parts for making these eskers work, and you just got to like play the clock forward for 1,000 years, and you will have formed an esker right near where you were standing. So
I trotted along the ridge of one to get a closer look at a glacier. It was driving rain, and you know, I didn't care. I put my stuff on, and we just went for a little quick jog, maybe a half mile or so, out to see the leading edge of this glacier that had formed this esker.
Cool. So you saw it happening in real time, esker deposition. Amazing. All right, Chris. Well, I think that's a wrap. Those of you who would like to support us, there's a couple ways to do that. You can go to our website, planetgeocast.com. There's a support us link there, and all of our old episodes with some transcripts, if those are helpful, and a little bit about us. You can also download our Camp Geo mobile app. We have a bunch of content with images. Basically, Chris, the intro to geology, the first year geology class you'd take in a college level geology major is there with a bunch of audio files, dozens of hours of content with a bunch of images that really, I don't know, geology is such a visual science. You kind of need the images to really understand some of these concepts we're talking about. We also have some audiobooks for purchase there. So go to our PlanetGeo app, download it, leave us a rating and a review. We really appreciate that. Send us an email, planetgeocast@gmail.com. We love getting listener questions and are always kind of putting together episodes based on some of them. And you can follow us on all the social medias @PlanetGeocast.
Cheers.